Welcome to Cloud Deck's video lessons. So, have you ever looked up at a completely overcast sky, one totally devoid of any visible landmarks, and wondered how in the world an aircraft weighing hundreds of tons can navigate precisely to a runway thousands of miles away? Well, it's not magic, even though it kind of seems like it. It's actually just a pure mastery of physics. Today, we're exploring the invisible highways of the sky. We're going to unpack the fascinating technology and techniques that allow pilots to navigate safely without ever actually needing to look at the ground.
Here is the roadmap for this explainer. We'll start with radio waves and propagation, move into ground beacons like the NDB and ADF, then tackle VOR phase comparison principles, distance measuring equipment, and finally wrap it all up with the instrument landing system.
All right, to truly understand the instrument sitting inside a cockpit, we first have to understand the invisible medium they rely on. Let's get into Section 1, Radio Waves and Propagation, or as I like to call it, the physics of the sky.
Okay, let's dive right in. The electromagnetic spectrum is incredibly vast, right? But aviation carves it up into very specific frequency bands, and each one has its own, unique superpower. Lower frequencies like the LF and MF bands, those power older systems like non-directional beacons. Moving up the spectrum, the very high frequency, or VHF band, is basically the sweet spot for VORs and ILS localizers. Then we hit ultra-high frequency, UHF, which handles your distance measuring equipment and the ILS glide slope. And finally, super high frequencies give us the crisp, high resolution needed for weather radar. And here's the crucial thing. Different frequencies literally travel differently through the atmosphere.
Think about it like this. Low-frequency ground waves actually hug the curvature of the Earth. That's what makes them reliable over certain distances, although, to be fair, they can be absorbed by terrain. Sky waves, which usually sit in the HF band, bounce off the ionosphere. This allows for transcontinental communication, but honestly, they are way too erratic and unreliable for precise navigation. Now, space waves. These are your VHF frequencies and above. They punch right through the ionosphere. They don't bounce at all. They travel strictly line of sight, which is exactly why your VOR or ILS requires you to have a clear, totally unobstructed physical line to the transmitting antenna.
Now, when we do talk about those bouncing sky waves, we run into a pretty fascinating phenomenon known as skip distance. I want you to imagine throwing a rock and skipping it across a pond. The rock touches down, flies up through the air, and touches down again further out. The space in the air where the rock is completely above the water, that's effectively your skip zone. If you happen to be standing in that zone, the signal is quite literally flying right over your head.
To really visualize that dead zone, imagine a transmitting station sending a signal up to the F layer of the ionosphere, which then refracts back down to a receiving station. But because of that skip, there's a massive circular area between them where nothing hits. That skip distance is entirely dependent on the ionosphere's critical frequency and the wave's maximum usable angle. If your aircraft is flying inside that skip zone and trying to tune into a skywave, you are going to hear absolutely nothing but static.
And that perfectly sets up how early aviators learned to harness these waves. Let's move to Section 2, ground beacons, NDB and ADF, the absolute earliest forms of radio navigation.
So the crucial concept here is understanding the relationship between the ground and the air. The NDB, or non-directional beacon, is basically just a ground antenna blasting out LF or MF radio energy in all directions. The ADF, the automatic direction finder, well, that's the receiver inside the aircraft. But how does it actually know which way to point? It's pretty clever. It uses two antennas. A loop antenna has a figure-8 reception pattern, which is great, but it has a 180-degree ambiguity, meaning it knows the station is on a specific line, but it has no idea if it's in front of or behind the plane. So to fix this, it superimposes a circular sense antenna over it. Combined, they create a heart-shaped or cardioid pattern with only one perfect null spot. That setup allows the ADF needle to definitively point to the station. But a quick warning, these low frequencies are heavily susceptible to errors. If there's a thunderstorm nearby, the ADF needle will literally abandon the NDB and point straight at the lightning strikes.
In the cockpit, the ADF gives you what's called a relative bearing, basically where the station is relative to your nose. But to actually navigate, you have to do a little mental math. Step 1, look at your compass for your magnetic heading. Step 2, read the relative bearing from the ADF. Step 3, add them together. Magnetic heading plus relative bearing equals your magnetic bearing to the station. So if you're heading 040 degrees and the needle points 050 degrees to the right of your nose, the station is at a magnetic bearing of 090 degrees. It's simple, for sure, but absolutely critical.
But how you actually fly that bearing matters immensely. Let's compare homing versus tracking. Homing is basically the rookie mistake of just turning the plane so the ADF needle is always pegged at 0. If there's a crosswind, it's going to blow you off course. And by constantly turning your nose back to point at the station, you end up flying this massive, inefficient curve. Tracking, however, means you calculate the wind drift and intentionally crab the aircraft into the wind. Your nose won't point at the station, and the needle definitely won't sit at 0, but you will fly a perfectly straight, super efficient line over the ground.
Let's look at the instruments themselves. On older setups, you might see a fixed card ADF. 0 is permanently at the top, representing the nose of your aircraft. With this, you have to do the math we just talked about. But look at the radiomagnetic indicator, or RMI. This is a massive upgrade. The compass card behind the needle automatically rotates to match your current magnetic heading. This means the head of the needle is actively doing the math for you in real time, pointing directly to the magnetic bearing of the station.
Now, while the NDB was a great starting point, the errors caused by thunderstorms and night effects really drove the need for something much better. So, Section 3, VOR Phase Comparison Principles.
Okay, let's really dive into this because VOR physics are incredibly clever. Think of a lighthouse. Imagine the lighthouse shoots a brilliant white strobe light in all directions exactly when its main rotating beam passes magnetic north. If you start a stopwatch the instant you see the white strobe and stop it when the rotating beam sweeps over you, that time difference tells you your exact angle from the lighthouse. A VOR does this exact same thing, but electronically. It sends out a 30 Hz frequency-modulated reference signal in all directions and a 30 Hz amplitude-modulated directional signal that rotates 30 times a second. Your aircraft's receiver simply compares the phase difference between these two signals to pinpoint your exact magnetic radial from the station. Honestly, it's brilliant.
To read a VOR, pilots traditionally use a course deviation indicator, or CDI. You dial in your desired course and the needle swings left or right to tell you where the line is. But there's a huge catch. The CDI is coordinate invariant. What does that mean? If you fly away from the station on a heading completely opposite to the course you dialed in, you get reverse sensing. The needle literally tells you to turn left when you actually need to turn right. Talk about confusing. To fix this, aviation gave us the Horizontal Situation Indicator, the HSI. By mounting the CDI deviation bar on top of a rotating compass card that's slave to your heading, the geometric relationship is always perfectly preserved. Reverse sensing is entirely eliminated.
So now VOR tells us our exact direction. But to know exactly where we are on our invisible highway, we need distance. Let's look at Section 4, Distance Measuring Equipment, or DME. DME operates up in the UHF band. Now, unlike VOR, which basically just passively listens, DME is an active conversation. Your aircraft sends out a paired pulse, an interrogation. The ground station receives it, waits exactly 50 microseconds, and fires a reply pulse back. Your aircraft measures the total round-trip time, subtracts that 50 microsecond delay, and calculates the exact slant range distance to the station. However, there's a quirk here. Because it's measuring slant range, if you fly directly over the station at, say, 10,000 feet, the DME won't read 0. It will still read over a mile. This inherently causes major errors in ground speed calculations when you get really close to the beacon. Also, notice it uses a random pulse repetition frequency. With dozens of aircraft interrogating the exact same station, your radio jumbles the timing of its pulses uniquely so it can recognize its own specific echoes coming back from the ground.
All right, now we have to actually land in the thick clouds. Everything we've discussed so far culminates in Section 5, the Instrument Landing System, the ultimate precision approach.
The ILS is basically two highly focused radio beams. First, the localizer operates in the VHF band and provides lateral, left-right guidance right to the runway's center line. Second, the glide path operates in the UHF band, providing a vertical, 3-degree slope straight down to the touchdown zone. Depending on the equipment quality on the ground and in the aircraft, ILS approaches are broken into categories I, II, and III, which dictate exactly how low you can fly before you absolutely must see the runway. And remember that reverse sensing we talked about? Sometimes pilots have to fly a back-course approach using the signal radiating off the back of the localizer antenna. If you use a standard CDI for that, you'll get reverse sensing. But if you have an HSI, you're perfectly fine.
As you ride that glide path down, the ILS system gives you distance checks using marker beacons. These shoot a 75 MHz VHF signal straight up into the sky. You hit the outer marker a few miles out. Your cockpit flashes a calm blue light and plays low-pitched dashes at 400 Hz. Closer in, The middle marker flashes amber with faster dots and dashes at 1300 Hz. And right before the runway threshold, the inner marker flashes white, screaming high-pitched dots at you at 3000 Hz. It's an incredible multi-sensory system designed to guarantee you know exactly where you are, down to the foot, without ever looking out the window.
And that brilliantly illustrates the sheer engineering genius behind instrument flight. We took invisible electromagnetic waves, accounted for atmospheric bouncing, built rotating phase comparisons, and developed microsecond timing loops, all to paint a perfectly clear picture on a 3-inch dial in the dashboard. So I leave you with this. Next time you're hurtling through the clouds in a crosswind, shooting a backcourse approach, will you remember exactly why that rotating compass card on your HSI is the best friend you have in the cockpit? Keep learning, keep questioning, and I'll catch you on the next explainer.